Hello everybody, welcome back to a new YouTube video, and today we are going to do a LeetCode problem. Yay! In my last video I made a binary tree class which uses a node component. We are able to solve these binary tree problems now. So if you guys want to see that video, I'll link it on the top right. You'll see me building this class and all its functionality. But basically I can set up a binary tree just using this list that I pass in. If I grab these numbers, we can make a binary tree off of these nodes. Let's just see it actually work in process, work for you guys. Output 9, 3, 9, 20, 15, and 7, 3, 9, 20, 15, and 7. So it works, guys. So today we are going to be learning about how to solve the problem maximum depth of a binary tree. So it says given the root of a binary tree, which is 3, this node 3, return its maximum depth. A depth is its longest path to its leaf node. So it says a maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. So what that means, guys, is let me draw a path for you guys. So these things are leaf nodes when a node doesn't have a left child or a right child. A left child of 20 is 15. A right child of 20 is 7. So this 9 is a leaf node because it has no left and right child. And if you go from 9 to 3, that's parent. If you guys know Roblox game coding, you do game and then just say this is the workspace or something, or this is replicated storage. We use that in Roblox coding all the time. But anyways, yeah, this is gonna be a parent node. This is gonna also be an ancestor of 9, and this 20 is going to be a descendant of 3. That's just some basic terminology. Anyways, we are going to try find the longest path from the root to the top. So this is one path, right? Let me just draw all the paths. So this right here is going to be a path of 2. This right here down to another leaf node is going to be a depth of 3. And then we have one more, which is this path. And this is going to be 3 as well. So looking at all these numbers, we have 2, 3, and 3. So we just need to return the maximum in this list that we made. So we would return this 3 or this 3. Doesn't matter, right? We just need the biggest number in these nodes that we generate. How do we basically solve it? Basically, we look to the left side first, right? And then I think we just run depth first search down through these depth first search until we find a leaf node. So when we find a leaf node, we calculate its maximum depth. Let's say we write a DFS function, right? And a DFS function, you need to give it a node. So let's say we have a current value that we're on, and then what we want to also give is the depth that we're at. So we would have a depth counter here because we would start. Let's say we're over here. What would our depth be, right? Our initialization process would be that when we start over here, we want to call DFS. Let's do at node 3, right? Let's just circle it to represent that as a node. So we're giving in the node and then we're giving a depth of 1. So this is how we would start off our code. Once we have current and depth, then we can say, okay, if our current node, right, if this 3, if we have nothing in the tree, let's say this is our tree with nothing, if there's nothing in this tree, then we would have to return 0, okay, because there's actually a value that says the number of nodes in this tree is 0, so we would have to return 0 since there's not anything in that in the tree. So if our current node, right, is null, then we would return 0. And that's our base case, right? So now that we have this little base case right here, we can just go on to the core of DFS, right? Else. So we're gonna write a recursive function to help us write this code, and this DFS function is gonna return our maximum depth. So we do something like that, and let's say we have a counter, right? Now we just need to calculate our depth. We got to know if we're at a leaf node. So I am now going to say is leaf, okay, for like it's a leaf node. So once we calculate that it's a leaf node, then we're going to return our depth number. So let's say we go here, then that's 1, okay, and then go down, that's 2, down. Actually, starting from here is 1, 2, and then 3. Okay, you guys can see that the height of this tree is going to be 3 just by looking at it. So when we're at is leaf, we're going to give back a value. So let's say we're over here, then we're going to return a value. Okay, so how do we know if a node is a leaf, right? We just check our current dot left is not equal null, and our cur dot right is not equal null. Then we could say, okay, this value that we have is a leaf node. So if it's a leaf node, then we would just return our depth. And what if it isn't a leaf node? So if we're like over here, then we gotta travel left or right, and we're gonna travel left first because that's a traversal way people usually do it. You go left first and stuff, and then you go right. If we return the depth, we actually want to return the maximum of this guy's tree. Okay, so what is the maximum height of this tree? Like we're over here, and then we're returning 2. So we want to return this guy's maximum and also this guy's maximum. So let's say over here is 2. This guy's maximum depth is 2, and this guy's maximum depth is 3. Okay, so then it's going to look like all we need to do is return the maximum of our left subtree and our right subtree. Okay, so that means DFS of left, the left side, I'm just going to say left, and then the DFS of right side. So if we get the maximum of these things, and we would probably want to also add 1 to here, right? Plus 1. Why would we plus 1 to this? It's because we need to give it our depth value as well. Sorry. Okay, because every time we call this function, we want to add 1 to how deep we are in the tree. So if you do this and then DFS the right side node, and then you give a depth of 1 plus 1. So we're going to get the maximum of this left subtree and the right subtree. Hopefully that makes sense to you guys. So then if we have this helper function, and if we do DFS, let's say we're given the root over here, we just start at 1. And then when we get to the second depth, right, over here, then it's going to give us the second layer or something like that. So hopefully this makes sense to you guys. This is the whole code. I'm going to start coding it up right now. What we need is to make a function here. This is DFS, and we give it our current node, and we give it the depth that we're at right now. Okay. And then we say if cur equals null, so none. If there's not a current node there, then we're just going to return 0. And then else we need to check if we're at a leaf node. So is leaf equal, we don't have a cur left and a cur right. So that means we don't have a node on its left child and a node on its right child. And then we say if is leaf, then we would return our depth. And then over here is our next case, which is, I don't really want to write that else, so we're just going to do this. It's because it looks cleaner, guys. And then we're just going to return our maximum of the left subtree and then the right subtree. I don't know if I'm explaining that correctly, but the maximum of this guy's subtree is going to be 3, and the maximum of this guy's subtree is going to be 3. Okay, and then it's gonna like compare which is bigger, this side or this side. It doesn't really matter which side's bigger, right? Because they're both 3. So we're just gonna make this guy's max equals to like 3. This guy is gonna be 2. We're getting 3 because we add 1 to the depth in the beginning. Okay, actually DFS cur dot left, and then we give a depth, and then we plus 1 to it, and then we do DFS cur dot right, and then we do depth plus 1. Okay, so this is the whole code. And then after we do this DFS function, we're just going to return DFS at root, and then we're going to give it 1. And if there is no current root, right? So if there's nothing there, and even though we start at 1, if there's nothing here, then we're going to return 0. But if there is something there, then we're going to return 1. So that works out well. So it should work, guys. Okay, yeah. And now we're going to code it in Lua. So we have this tree. So then we're going to make a function here called max depth, and we're going to give it a root. And then we're going to want to set up this value max depth and tree. We have a root value here, right? In our tree. Let me just check. So then we have a root value. Okay. So we given a root over here to our max depth function. It's going to print out 3, hopefully. So we're going to make a helper function, which is our DFS. And this is going to take in a current value and then our depth value. And then we're going to return DFS root and also 1. Okay, here is we need to check if there is a root. So if cur is equal to nil, if not cur, then we say return 0. Else, what we're going to do is we are going to check if it has a leaf, is a leaf node. Cur dot left does not equal nil, and cur dot right does not equal nil. Then if is leaf, then we would say, I'm gonna copy what we did in Python, which is not cur dot left and not cur dot right. So if there's no value for the left and right node, then we know it's a leaf node. So if it's a leaf node, then we would return the depth that we're at, and then we would say we would return the maximum math.max. Hopefully it returns its value, but I'm not too sure. Actually, we're returning the depth, so it's going to be a number value. So we can just say DFS cur dot left and then depth plus 1, and also DFS cur dot right and depth plus 1. So hopefully this should work, guys. This looks like the whole code. We checked the left guy's side, and then we recurse through, check the right guy's side, get either the left guy's subtree maximum, which is 2 or 3. So we run it, and then it should be 3. So yeah, it works, guys. This is the Lua code. I didn't really go over runtime, but it's going to be, I'm just going to say O of n, because n is like the height of the tree, right? Because we got to travel through all these nodes to find the biggest height of the tree. So for each node, we add like 1 to the depth or something like that. If we go down a layer, we got to check this node, we got to check this node, this node, this node, this node. Actually, I don't even know if we check this node first, because we start at that node, so it might be n minus 1, but it's still n, which is constant time. And the memory, our memory is going to be the height of the tree, so it's going to be O of n as well, because we're keeping a recursive stack or whatever. And if we do DFS at the first node, DFS at the thingy node, this call stack is going to be how much space we need. So that is space complexity. And we are going to just check it with this one as well. So we have 3, and then this should give us 2. So hopefully you guys enjoyed that episode, and I'll see you in the next one later.